Hey guys, I'm actually going to try to make a different video today using different hardware. I got this new tablet thing, and I got this Yeti microphone, and I hope this turns out all right. And I'm going to use this to try to make this video on linear programming. And by the end of this, you should be able to solve a problem using linear programming. So that's our goal by the end of the day. And what is linear programming, you might be asking? Well, linear programming is a mathematical method that uses systems of equations, not always linear, but in our situations it will, that statisticians, businesses, anyone can use to maximize and minimize certain things, which often is things that need to happen in businesses and real life situations. So let's start just by defining linear programming. Okay, so blank is a mathematical method. Well, linear programming is a mathematical method for determining a way to achieve the best/worst outcomes, such as maximum profit or lowest cost. So we're trying to max those out or minimize one other thing in a given mathematical model. Okay, that's what linear programming is in a nutshell. And so really what we do is we're going to take this problem right here, right below here, and we are going to try to maximize the profit that this company can make using this mathematical model given to us right here. So let's start this off. The step number one is to go through and read these problems and highlight any important information. So I'll read the problem once and let's go through and then highlight the important information. A company manufactures scooters and skateboards. The factory has the capacity to make at most 6,000 scooters. So we got a limitation there, 6,000 scooters in one day. And the factory can make at most, another limitation, 8,000 skateboards in one day. Okay. However, the factory can produce a combination of no more than 10,000 scooters and skateboards. So altogether, they can't make more than 10,000 things. So no more, another limitation of 10,000 scooters and skateboards together. Okay. So there it looks like that's the important information. And now let's start to define these variables. Well, it looks like there's two things that can vary. We can vary how many scooters we make, and we can vary how many skateboards we make. So let's let x, one more second. Oh, that's wrong. Let's let x, go back here, equal the scooters. And let's let y equal the skateboards. Now, when I may say scooters, is number of, right? Number of skateboards. Okay. So now that we have these variables, the next thing we want to do is set up our inequalities. In other words, we want to come up with what are our limitations. What are our limitations? So maybe put a word up here. Inequality is the same thing. Think limits. Hopefully I spelled that right. So let's take a look and find some limitations that were given to us. One thing it says we can only make at most 6,000 scooters in one day. So if scooters has to be less than or equal to 6,000, right? But scooters isn't really scooters. We define scooters as something else. We defined it as X. So we'll put X in for that. So we know that X has to be less than or equal to 6,000. And the same goes true for skateboards. Here, you can make at most 8,000 skateboards. So we know another limitation is Y, which is our skateboards, right? Has to be less than or equal to 8,000. So that covers this limitation here and that limitation there. We also have this limitation. They can produce a combination of no more than 10,000 scooters. And skateboards, together as a combination. So the most they can make of anything altogether is 10,000, and that's a combination of both skateboards and scooters. So we got X plus Y must be less than or equal to 10,000. Okay, so we have our inequalities. Now, since we have our inequalities, our next goal is to graph those inequalities. So let's start by graphing the X is less than 6,000. What would that line look like? Let's do that one in purple. I'll highlight that purple. Well, that would be a vertical line because this X is less than, and it would be a vertical line going at 6,000. Right there. Here's our vertical line. I'll draw as good as I can right there. And we know that we need a shade on one side of this because it's inequality. And because all the values of X are less than 6,000, is 4,000 less than 6,000? Yeah, it is. So we would shade this way. And so what I like to do, just keep track of it, is I like to put little dashes, really small dashes to keep track of it all. Okay, we would be shading this way. Now let's do the y is less than or equal to 8,000 right there. So that's going to be a horizontal line at a height of 8,000, right? And we are going to graph so y is less than that, and 6,000 and the situation is less, so that kind of tells us we would graph below this situation. So we're going to graph this way. I'll put a little dashes, just keep track of which way we're going to have to shade that side. And the last situation is this one right here. We'll do that one green. X plus y has to be less than or equal to 10,000. Well, in this situation, to graph this, we might want to solve for this y so we can graph a little bit easier. So I'll subtract this x and put it over on this side. So I have y is less than or equal to negative x plus 10,000. So right here, this 10,000, that's your starting point. So we're going to put a dot right here at 10,000. And this negative x is your slope. So we go down 1 and over 1, or we could go down 500 and over 500. It's the same idea, right? Down 1 over 1, down 1 over 1. Follow this pattern on and on forever and ever. Well, not ever and ever. That would take for a while. But this is good enough right there. And so we will graph our little line right there. Now, which way do we shade this line? Well, we know y is less than that, so we have all the values that are less than that, so we would shade this way. So, what we're trying to do right now is bring together something called the feasible region. And this feasible region is the region that all of these inequalities are going to be true. And in that situation, our feasible region is where we graph all these. So we have to graph below. Let's start with the red line. We have to graph below this red line, so this is not going to be shaded. We know we have to graph to the left of this purple line, so this is not going to be shaded. So it looks like we're in this zone right here. And we have to graph below this green line, so it looks like here's our feasible region. I wish I had a, let me see if I can get a nice color here. We've got this one, transparency, color effects, transparency, put in the middle. Make it yellow and solid. So let's see if that works. Yeah, there we go. So here's our feasible region right there. There we go. There's our feasible region. So right now we just put together our feasible region of what this company can produce. We haven't even gotten to the linear programming part. Let's take a look. There's another part to this that gets to that. Okay, so the next question part that's going to go off of this is the company makes a profit of $15 per scooter and $10 per skateboard. How many of each should the company make to maximize its profit? So that's the question now, knowing there's $15 per scooter and $10 per skateboard. So what we need to do is we need to come up with an objective equation. And our objective in this situation is to maximize profit. So I would start this off with putting maybe a P. Our objective is to maximize this profit. We want to make this P as big as we can. And the profit really is equal to $15 per scooter, $15 for every scooter we sell. And if I remember correctly, our scooters is X. Yep, it is X. Just had to scroll up just to make sure of that. So 15 times how many scooters we have, plus $10 times how many skateboards we make, which is Y, should give us our profit right there. Now, what do we do with this objective equation? Well, we got to figure out which of the situations up here will maximize this. Can I make would it maximize my profit to make 2,000 skateboards and 2,000 scooters? Or maybe 4,000 skateboards and 4,000 scooters? Or maybe this right here, 6,000 scooters and 1,000 skateboards. Which point in here would maximize our profit? Well, there's infinitely many points, right? So the question is, which one do you choose? And this is the key to it. To maximize or minimize profit, you need to test the corners. Okay, that's the goal. You need to test the corners, and I'm going to put this in here, and use common sense. Okay? Let's use common sense, and I'll talk about that while we're doing this, okay? So let's choose some corners here that we're going to test out. Well, let's start with this. The corners of the feasible region right here. Here's a corner, there's a corner, there's a corner of the feasible region, there's one, and there's one. And we're going to test those. But some we're not going to test because they don't make sense. For instance, let's look at this one. If we sold 0 scooters and 0 skateboards, would we make any money? No, that doesn't make sense. We won't make any profit off of that. So we're not going to test it. We're not going to waste our money testing that one. Now let's take a look at this one. What about, should we test this point right here where we sell 6,000 scooters and no skateboards in this situation? Well, some people might say, yes, we should test that point. But look at this point right over here. This point you sell 6,000 scooters just like this one, but you also sell 5,000 skateboards, right? So wouldn't it make sense that this point right here would make more profit than this one right here? Totally would, right? So we're not going to test that one. And the same holds true for this point right here. Here, these 2 points, we both sell 8,000 skateboards, but this point right here, we actually sell some scooters. So we're not going to test this one either. The only 2 points that it makes sense to test in our scenario are these 2 points right here, this one and this one. So the 6,000, 5,000 point, 6,000 scooters and 5,000 skateboards, and the 8,000, or sorry, the 2,000, 8,000 point. One of these two will maximize our profit. We just got to figure out which one. So let's just write those 2 points down here in a nice organized fashion. So we got 2,000, comma 8,000. And then we have this point right here, 6,000, 5,000. Okay, right there. And now what we're going to do is we're going to take these 2 points and we're going to plug them into this equation. That's what we're going to do. And one of them's going to, each of them is going to give us a profit. We're just going to figure out which one's biggest. And then we've maximized our profit. We know that we would sell that much. So let's start with this one. We're going to take this 2,000. Let's plug this in as red. Okay, this will be our red one. Red. So we got 15 times 2,000, because I plugged the 2,000 in for the X, plus 10 times 8,000. Well, 15 times 2,000, what would that be? 30,000? Plus 80,000. 30,000 plus 8,000 is 110,000. 110,000. So our profit, if we were to sell 2,000 skateboards and 2,000 scooters and 8,000 skateboards, would be $110,000. Nice chunk of change right there. Okay, so that's this one. Let's test one more. Let's test this one right here and see if this one will outdo this profit. Okay, so we're going to plug this in the same equation. So we got 15 times 6,000 plus 10 times 5,000. Okay, I know 10 times 5,000. Oh, I put too many zeros there. 10 times 5,000 is 50,000. I was just thinking, I must have been thinking about that in my head. And 15 times 6,000, that's 6 plus 90, that's 90,000. Right there. 90,000 plus 50,000 is $140,000. I'll put that right up here. I'll put it down here too, just because we're taking good notes right now. So if we want to maximize our profit, which scenario would we want to use? Would we want to sell 2,000, again, I'm forgetting, 2,000 scooters and then 8,000 skateboards, or 6,000 scooters and 5,000 skateboards? Well, this one gives us more money, so it would make more sense to do this one. And so using linear programming, we figured out how many scooters and how many skateboards we should sell to maximize our profit. The situation is 6,000 scooters and 5,000 skateboards. So that's the flow of how you can use linear programming to maximize profit in certain situations. Is this a very simplified linear programming problem? Yeah, it is, but this is the first time you guys have done it. So I'm not going to give you anything terribly complicated. Not saying that this isn't hard. This is still a hard problem. In the real world, though, these equations that they're using are a lot more complex. But they're definitely useful in the real world. So this is something you're going to have to practice a lot. And hopefully my activities that I put together will help guide you through the steps in the process for doing problems just like that. Don't be scared to ask questions on this. It is hard.